I think I need a little quiet moment because I sense a spirit flicking through the room. And I would like to see if we can call him. Maurice, can you hear me? Maurice? Yes, he's here. Do you have anything to say about bugs? As soon as we started programming and running programs, we found to a surprise that it wasn't as easy to get programs right as we thought it would be. You know, even the moon had to be discovered, and debugging had to be discovered. And I can remember to the exact instant. The tape equipment was on one floor, the computer was on the other, and I was passing down from the computer to make a change to my program tape. And that instant, I realized that a large part of my life from then on was going to be spent in finding mistakes in my own programs. And there's another. I think, yeah, this is Betty. A number of us worked with Dr. von Neumann in setting up this code, and it was to be set up with dialing into the function table, which had settings from 0 to 99. We felt we would need that many settings for all the instructions. We sort of worked along for a while, but to my astonishment, he never mentioned the stop instruction. So I went to Princeton with the idea that I have the courage to mention a stop instruction. So I did kindly say, don't we need a stop instruction in this machine? He said, no, we don't need a stop instruction. We have all these empty sockets here that just as it go to shut down. So I went back home, and I was really alarmed. After all, we had debugged this machine day and night for months, just trying to get jobs on it. So the next week, when I came up with some alterations in the code, I approached him again with the same question. He gave me the same answer. Well, I really got red in the face. I was so excited, and I really wanted to tell him off. And I said, but Dr. von Neumann, we are programmers. We sometimes make mistakes. So he nodded his head, and the stop order went in. Dear colleagues, thank you for letting the dead speak from beyond. They were Maurice Wax, born in 1913, dead in 2010, designer of the EDSAC, one of the first computers, and Betty Snyder, by her married name Holberson, born in 1917, died in 2001, one of the 6 lady programmers of the ENIAC. As for me, my name is Laurent Bossavit, and thank you. Why you are thinking did I want to start with calling on these voices from beyond, these pioneers of the computing age? Well, because this conference is called NewCrafts, right? And the opening keynote was faithful to this theme. It was all about what's new today, and everything is changing around us so fast. The things that astonished us only 3 months ago, that's yesterday's news. You should see this week's ChatGPT demo, right? And yet there is one thing that does not seem to be changing, that is still with us, as it was in the 1950s. Bugs. So I want to try something and have a quick show of hands. Can you raise your hand if you think you are seeing fewer bugs today than you did at the start of your career in programming, whenever that was? Ever some optimistic people. Can you raise your hand if you think that's the opposite, it's getting worse? Okay, so I get the majority is shy. That's fine. Anyway, a few years ago, I decided that this was one of the most important questions in the business. Where do bugs come from? And I come back to it from a fresh angle every few years or so. So I thought it could be a good idea to check if this is still a useful question in the age of AI. And when I say where do they come from, I think that's the interesting question. Just realized I completely forgot to show you the images of the spirits. So that's Maurice, and that's Betty, and that's me, and that's the slide we are on now. It was the first time I tried spiritism on stage, so I got nervous. Anyway, where do bugs come from is the important question. Not so much what do we do with them. What do we do with bugs? And louder? What do we do with bugs? Sorry, no, that's the wrong answer. I hate to be judgmental. We fix them. That's the only useful things to do with bugs once we have found them. Yeah, no, that doesn't work either. Sorry. No bugs. That's going to be my motto. But yeah, it's not even very hard most of the time. It's a fun activity. I like debugging. But if we had a good answer to the question, where do bugs come from, we could perhaps, just perhaps, prevent them from happening in the first place. And maybe save lots of time. So for many years, I thought that the place to go to find answers to that question was the human brain. I said for a while that bugs in the code come from bugs in the brain. And by bugs in the brain, what I'm referring to is this fascinating category of cognitive biases and fallacies. And Diana alluded to that yesterday in the closing keynote when she talked about improving our system of thinking. I'm going to be referring back to that a few times. And those problems with our system of thinking have been studied systematically for only a brief time since the work of Kahneman and Tversky, who started work in the late 70s. And if you haven't read it, Thinking Fast and Slow is a very good introduction to this body of work. Modern humans have been around for 150,000 years, give or take. And that's the age of the version of the brain, of our operating system, if you will, that we are still using today. And we've had lots of updates to the software, so to speak, but the bugs are still the same. It's still the same version. That's a metaphor, by the way. I'm not saying we are literally computers. The point is there are very old bugs, and we have only discovered them in the past few years. I was not sure I was going to include this joke, but if you know about the exponential cost of bugs given on age, you can imagine how expensive those are going to fix. But anyway, thinking about those cognitive biases was very useful to me professionally for a number of years. It gave me a handle on test-driven development. It gave me some workshops and talks at conferences, for instance, The Art of Being Wrong. And indirectly, it led to my book, The Leprechauns of Software Engineering. But that was 10 years ago. And I have moved on to a new phase of thinking. And in that new phase, I no longer think that the most important thing is to look at the bugs that happen in a single brain. I think it's crucial to look at two brains at least, and what passes between them, basically at failures of communication, which was Woody's theme earlier. Has anyone been in Woody's session? Enough. So we'll have occasion to refer back to that. And we've been communicating as humans with modern human brains for, again, at least tens of thousands of years. It's not easy to date back the origin of speech, because we only know how to date things when writing appears. But there are studies. But anyway, we know that bugs occur in communication, right? Anyone disagree with that? And we still don't even have a name for these bugs in the same way that we have the name cognitive biases for bugs in the brain, and let alone a scientific theory of bugs in our communications protocols. A few people have tried. For instance, this is Alfred Korzybski, managed to pronounce that, who invented something he called general semantics. One of the famous sayings was, the map is not the territory. You may have heard that. His ideas never really caught on. He had successors, people who explored those ideas, and one book I actually recommend is This Language in Thought and Action. I was very disappointed yesterday because as I remembered it, I thought the cover had a picture of an iceberg. But there you go. His ideas never really caught on. The book is brilliant, but it did not rise to establishing a science, a research program, in the same way that Kahneman and Tversky established the cognitive biases research program. But we do have practical ideas that come from this notion of communication failures. An illustration I like is this one from Jeff Patton, where you have a group of people who are all in agreement, nice, consensus. The problem is they're agreeing on different things. Anyone have this problem? Anyone have this problem in software? This is actually a big problem in software teaming. It's a problem in communication between PO and dev team. It's a problem within the dev team. The French word I use for this quality is cohérence. But a good term that I'm going to borrow from Diana's keynote yesterday is conceptual integrity. It's about the same. And my favorite laboratory for investigating the consequences of failures in conceptual integrity is something we call the coding dojo. Anyone heard about the... Thank you. This is something that a group of us invented. I was kind of at the forefront of that with my friend Emmanuel Gaillot, Manu, si tu m'entends, just about 20 years ago now. If you want to feel old. The point of software teaming or of a coding dojo is to come together as a group and solve a programming problem as a group. So we show the code on one big screen, like this one, or a bit smaller, and everyone is looking at the same screen and sitting side by side and working on the same thing. In the coding dojo, as originally designed, we worked on exercises called programming katas, a term we borrowed from the martial arts. The dojo was meant as a teaching and learning space only, not for working on production code. The katas were problems already solved, in a sense. We were not interested in figuring out the solution to the kata, the algorithmic solution. We were interested in achieving a precise gesture in good form. And the way that you get a precise gesture in martial arts or practically anywhere is by repetition. So we would solve the same katas over and over again. Now, in a dojo, what you can see is different people approaching the same problem from different angles. And that's great, because diversity is a strength. It's going to lead to robust solutions. But at the start, what you see is kind of a mess. Let's say that the square person is the object-oriented fan, right? So you've introduced the problem, and they start thinking about what classes they want to bring, how they want to name them. The circle person, I made a note yesterday that I was going to be careful not to call them the person that goes in circles. Anyway, they are the experts in algorithms. So they start thinking about edge cases. And maybe the triangle person has been trained in test-driven development. And so the first thing they think about is a test. Yay. But you can guess what's going to happen. They're going to clash a little bit. It's going to take some time before they actually start to make progress on the problem. And a lot of the time what happens in the coding dojo is we get to the end of the 2 hours and we have not solved a simple exercise in 2 hours. We want to laugh at them, right? Haha. But if you think about it, you know what's worse? It's if these 3 people were each working in isolation, because then they would not realize that they have extremely different ways and incompatible ways of approaching the problem until it was much too late. And then you have to do everything over again, or worse, keep carrying on the technical debt. So, by way of making you feel what conceptual integrity can be like, I want to start from a story that happened in an actual coding dojo a few months ago. And we had chosen a kata called poker hands. We have, I got props now. We have hands of poker, and we want to see which is the winner. So, historically, the dojo was founded by people who liked extreme programming, and so we start with a test. And that's the test. The language here is Haskell, which will be important later, but if you don't know the language, it doesn't really matter. There is only a tiny amount of code. I will be explaining all of it. I hope that doesn't scare anyone. And we have only 1 line of code. It's not even a line of production code. It's a line of test code. But there can be a lot going on in 1 line of code. A lot of room for failures in communication or breakdowns in conceptual integrity. So a lot of room for bugs to creep in. We're writing a test, so we are designing API first. We are thinking in terms of usage, and we have a function called winner. That sounds reasonable. Should be is a word that says this is the result we expect, and we are saying this could possibly be improved upon, that the hand on the left is the winning hand. I hope that's correct. The first potential problem that was apparent to me anyway, because other people in the dojo may have had and probably had different perspectives, but the thing that I started thinking about was these 2 strings. You see how that could lead to problems? That we have text strings to represent poker hands. Yes? So we are in France. We could have, for instance, chosen to use the French name for the suits, like cœur and carreau. But then those have the same initial letters. So being smart, we decided to go with English, where hearts, diamonds, and spades and clubs each start with a different letter. Crisis averted. And then we have choices to make about the values as well. Because, well, the 1 is that 1, as in the number 1, or A, as ace. Same goes for the 10, which is actually 2 digits if we want to use a 10. And we would like to get away with using only 1 digit. And we can use a 0 or T, choices. And then, of course, we are diligent about recording our decisions, so we write a comment, problem solved, right? That doesn't really solve the problem, But really, what is the problem? One way to look at it is that every piece of code that touches the strings is going to have to take a decision. Is this a valid representation of a card? And okay, if we're going to write code that does that, then we are going to be writing more unit tests, right? But that's a lot of unit tests to write, and we are lazy. It's a virtue of programmers. But what's the root of the problem? It's like if we were moving up or down the iceberg. Where does the problem come from? It comes from a mismatch in what we're trying to represent, the universe of domain objects. And these are domain objects. Nothing on the screen is a domain object. This is. And what we've chosen to represent domain objects with, which is strings. So how many, I've given away the trick. The trick is counting. How many cards are there in a deck of French cards? 52, 53 if you count the joker. And how many two-character strings can you make? Yeah. So how many single character in the, so let's say we're using ASCII, huge cultural assumption, but let's say we're using ASCII, that's 256 possibilities. So we have that squared, and that's 65,000, give or take. That's way too many. Even if we choose to use only digits and letters, that's 36. And 36 squared is, I cannot actually calculate that by hand, but it's 13,100, sorry, give or take. See, way too many. So what do we do? Turn the page. We focus on this challenge of reducing the conceptual gap between the representation and the domain objects. And let's start slow. So we're going to start with the joker. And really, the syntax doesn't matter, because you see what's going on here. We're saying we've introduced a data type, which is called the joker, and it has one value, which is the joker. That works. It's, the saying about some code has no obvious bugs, and there is code which is so obvious that it's clear that it doesn't have bugs. I'm making a mess of it. But this is it, right? So let's go on to something harder. We're going to do the high cards. Okay, 3 high cards, 3 values, and we call that a high card. Everyone ready to move on to the low cards? No? So in the dojo, we can take questions, and we make sure that everyone stays on board with whatever is happening. That's part of the rules. But this is a timed speech, so I need to rush a little bit. And there's another reason I want to rush, actually. So you will allow me. It's not like you have a choice. Let's deal with the low cards. And there's 10 of them, so we have 10 values. I've snipped a few. And now we're going on to the next trick. We're going to get the low cards and the high cards together in one new type. And we call that a sum type. Why do we call it a sum type? Because the number of values that can be in a sum type is the sum of the types, of the number of values in the types that make up the sum. Neat, tidy. And we have the same with product types, where the number of types that can go into, the number of values, sorry, that can go into a product type is simply the product of the number of values that can go into the types that make it up. So here we have 13 values that can go into a card value. We're going to move on to the suits, and there are 4 values. And this is a product type. It's simply a pair, right? So it's a pair of a value and a suit. So how many values are in there? 52, exactly. And we know this. We can see this And we can know this. We know this is correct. No, it's not correct because I forgot the joker. So here it is. And so we are going to add the joker to that. So we're going to have a sum of a product of two sums. It gets a little bit complex now, but we can still follow along and see that it's obviously correct. So collectively, sum types and product types are known as algebraic types. That's really not important right now. The important thing is to notice that we have a model of the core domain. And by having a model of the core domain, we have eliminated altogether a whole category of bugs where we have something which is not a legal value for a chord. So there's a catchy phrase for that, which you don't have to memorize or even note because we'll come back to it, which is make illegal states unrepresentable. And the other key idea is that we have reinforced the conceptual integrity of the domain, but we have also reinforced conceptual integrity within the team, within the group of actual human beings looking at this code, who built it together. Well, that's an idealized fantasy version of what I wish would have happened that night at the coding dojo, remember? So I'm not saying this always happened, but it's a direction, it's where I want to be headed. And with all this, we still have only one unit test. It looks like this now. I agree, it's a little bit unpleasant. And we get there because we thought using strings was going to be a problem. But actually, strings are easy to read. That's one of their appeals. So we can introduce a couple extra functions that go from a string to a card and the other way around. So now we can have our cake and eat it too, so to speak. We can have a nice and tidy representation, but we still have this guarantee that invalid card values are not going to sneak into the program. And what we are doing here basically amounts to that, to having drawn a nice boundary around the core and establish a point of passage where to get inside this core, you have to go through the function that checks whether it's a valid representation of a poker card, and that is parse. We know this principle as, with a little bit of approximation, a functional core imperative shell. Actually thinking of this as being in Haskell, which is not an imperative language. But the idea is whatever happens at the edges is not really so much a concern because now we have this nice core. As an aside, think about the security implications. We know that text strings often contain a lot of crap. For instance, SQL injection attacks. And when the boundary is that well defined, you can rest easier knowing that anything that comes into the core gets inspected, for instance, for possible injection attacks. So that's another win for conceptual integrity. It's also a win for security. So we have eliminated a whole class of bugs, but we also have less code to worry about and test because there's a single place in the code where we check for the validity. So we've also simplified the system. And so the way I think about this in terms of heuristics is parse, don't validate. And that's actually the title of an article I keep thinking about that inspired this whole talk. And I think this is where we see a whole new magic trick. Because these principles, these guidelines, these heuristics, they are not tools in this, they are not recipes that you apply without thinking. there are things the team has agreed to talk about, agreed to use, and so there are essentially bits of a new system of thinking, to come back to Diana's keynote, for the team. And it's interesting to think of this system as a system. So we've seen 3 parts of it, but there's more. If you think back on bugs that you've seen, actual bugs in object-oriented code, a lot of them come from modifying state. If my playing cards were classes in an object language, I would have setters and probably also getters. So I could conceivably make it so that the system, the classes, the objects in memory had, for instance, 2 jacks of hearts. And that would be an illegal state. So by manipulating state, we are able often to introduce illegal states. And that goes against the intention that we had when we started thinking about trying to do things in a functional way. So we have other bits of the system of thinking that come along and that are related together, so they are kind of dragged into this. Some types and product types, which I already talked about. This notion that state is evil, and the way to avoid state is to use mostly pure functions. And pure functions are easier to unit test, so we spend less time worrying about how to write the unit tests. And we have immutable objects, and these things interrelate. So the overall system has its own conceptual integrity. One criticism I got from an earlier version of this talk was, I didn't give you any examples of all that, but think of this as a freemium model. This was the free sample, if you want more. I'm not selling anything to you, the cost is time. If you want to know more, you can learn more, and let's talk about it. But my point that I've been trying to make all along is that when you ask, where do bugs come from? When you take that question seriously, the answer does not have anything to do with tools or practices. Bugs come from failures in communication caused by defects in conceptual integrity in the shared mental models of the team. And this is the part where this talk checks the box, which is now obligatory for getting funding or presenting at a conference. Yes, I'm going to talk about AI. But actually, it does connect. We can circle back to AI and large language models and think about why they cannot be the magic wand that solves all of our problems with coding or debugging. What is an AI, or more specifically, a large language model? It's a big pile of linear algebra per XKCD, so that's from 2017, a little bit ahead of the curve. And we steer and steer until it starts giving us answers that look correct. But these piles of linear algebra are the works of humans, so they have bugs too, right? What's happening with generative AI is that we're going to have a situation in which we have a new class of things that generate code in addition to human brains. And we will have to communicate somehow with that class of things. Prompt engineering, in a way, is that. It's people learning to communicate with this new class of entity. Is there something more to it than stochastic parrots, as the saying goes? Things that just repeat in a statistically plausible way. They're training data? I don't know. But for sure, if we're going to use the code, or even sometimes ask the LLM to fix the code that it's just produced to us that we've seen is wrong, we're communicating. So obviously, we are going to have communication failures with this thing too. There's no going around that. So we have actually introduced a new source of bugs, which is why I don't think that LLMs are in any way, shape, or form a magic wand that can solve all of our problems together. But I don't think that functional programming either is a magic wand that we can wave at bugs and they will magically disappear. There's still work involved. What I do believe is that by improving our thinking, and specifically by talking as a team about our heuristics, about our guiding principles, that discussion is a high leverage activity. It will improve the conceptual integrity of the team. It will improve our effectiveness and our efficacy. And then hopefully improve our capacity to catch bugs before they are introduced. So the true source of bugs lies in the nature of human experience and communication. And each human experience is unique. This diversity is the source of much failure and misery, but it is also our greatest strength. So that's where I want to leave you, hopefully with a more skeptical and critical outlook on AI and LLMs, but also with great hope in the human condition. And whether or not I have achieved this, I end here, and thank you for your attention. One more thing. If you want to get this talk, or at least an earlier version of it on the Dead Trees edition, it's in the upcoming Programmé magazine. So that's obviously only going to be worthwhile for people who are in Paris, but for the rest of you, it's a great excuse to stay in Paris for a few more days. Just saying. I'm really done, and I was going to say at the start something like, I don't want to take questions. I do want to take questions, but just for this once, if you have a question, if you have a remark actually disguised as a question, feel free. Do not even disguise it as a question. But specifically, I'm interested in anywhere I went too fast and you would like to come back to and take the same step more slowly. But anyway, the floor is yours now.
The same goes with the AI. So the more, the more you manage to talk in using standards and precise naming with the AI, and the better the communication will be. So yeah, just it's not really a question. Just
I'm extremely cautious around words like communicating with the AI, because that presupposes something. I think it's a pile of linear algebra, and there is no understanding that goes on in there. But that's a kind of a personal, almost a faith thing. But yeah, why not? I mean, communication is communication. So what I do know is failures are going to take place. So I was almost hoping that no one would have any question, because then I would have repeated one of Woody's jokes and said, oh, okay, so if everyone thinks they have understood the talk, then you have misunderstood it. But I'm glad that there was one question. Another? but that doesn't let you off the hook, right? There have been multiple failures in communication in these past 40 whatever minutes. So, Cyril? Absolutely not. Did everyone get that? So do we have, in order to have conceptual integrity, do we have to be basically clones of each other mentally? Absolutely not. Because we still have that diversity, because we are still seeing things from different perspectives. But that's the interesting thing. I call them guidelines or heuristics. And that's kind of a very deliberate choice of word. They are not processes or rules or even practices. There are things that we have a rough and ready agreement on, but everyone on the team is going to develop their own individual understanding of what parse don't validate or functional core imperative shell means. And that's the beauty of it. We don't have to have perfect alignment on understanding the things. We just have to say, we understand how this is supposed to get us what we want, which is fewer bugs and happy customers and happy users. And because we are supposed to understand how that goes, we are relying on our own mental models, individual. But we have reached an agreement to go in that direction via a certain route. And we hope that this will help us get there faster. And if that's not the case, then we will revisit. That's all. I feel like I'm repeating Diana's keynote, so I'm not going to go on with that. But thank you very much. And if there are any more questions or people who want to learn about functional programming, come and see me. Thank you.